Hey everybody, welcome. Today we're going to talk about how Ubisoft and Behaviour Interactive migrated game server infrastructures to the cloud using low-cost, dedicated game servers with Amazon GameLift. My name is Bruce Brown. I'm the Software Development Manager for Amazon GameLift, and with me today are Fadi Beyroudi, Technical Director for Behavior, and Laurent Chouinard, Services Producer of Ubisoft. So what are we going to talk about today? Three things, essentially. Why is the industry shifting to dedicated game servers? How do you build infrastructure for dedicated game servers cost effectively? And what do GameLift customers have to say? We're going to hear from, as I mentioned, Behavior and Ubisoft. So why dedicated game servers? Well, dedicated game servers have some key advantages over peer-to-peer. First, there's no client-side cheating. With dedicated servers, all players connect to a server in the cloud, so there's no client host. This eliminates hosts cheating by manipulating the data being shared with other players in the game. Next, there's no NAT traversal. With dedicated game servers, home networking configurations can no longer block players from being able to communicate with one another. Third, there's no host migration. Host migration, when a host disconnects and data has to be migrated to a new host, can interrupt gameplay and is non-trivial to implement. With dedicated game servers, again, since there's no host, there's no data to migrate if a player disconnects. Lower, more consistent latency. Dedicated servers can, perhaps surprisingly, have lower latency than peer-to-peer. Our customers will talk more about their data on this topic later. And finally, larger numbers of players. Dedicated servers can scale to manage hundreds of players, whereas game clients are limited by the client hardware. So dedicated servers essentially address all these problems, and as players demand better multiplayer experiences, the expectation bar has gone up, and dedicated servers are becoming a requirement. So what's Amazon GameLift? Amazon GameLift provides dedicated game server hosting in the AWS cloud and has four essential value propositions. First, low-cost game servers. We leverage all the capabilities of the AWS cloud to provide the lowest cost game servers in the industry. Second, low latency game servers. We support 15 AWS regions with more on the way, providing you game servers where your players are globally. Third, high availability. You can run your game from any number of our 15 currently supported AWS regions, ensuring that your game is always available to players. And fourth, flexibility. GameLift has a number of managed options, from a fully managed solution that abstracts away the underlying AWS primitives, which I'll be talking about mostly today, to the ability to lift and shift your current game server management infrastructure directly into AWS. I'll be touching on that one a little bit later in the talk. Before we dive into the fully managed GameLift service, let's talk architecture of game services for just a moment. So first, you have a place where your infrastructure is operated. That could be an on-premises data center, a colo provider, or the cloud. And that infrastructure is generally made up of three large pieces. First, a gateway to your services. Second, the services themselves. And third, game servers. The gateway generally provides a mechanism to protect your service from denial of service levels of load. It provides a scalable load-balanced service to host your services API. And it provides a mechanism to authenticate users to your services. The services themselves provide basic multiplayer game support like matchmaking, session directory, player data, and player analytics. And then there's generally a service to manage connecting players to game servers. In the AWS cloud, the gateway services include AWS Shield for DDoS protection, Amazon API Gateway to host API, and Amazon Cognito for authentication. The services could be AWS Lambda-based services that provide serverless, scalable, and flexible compute, or feature-specific services like Amazon GameLift FlexMatch. And finally, Amazon GameLift is the AWS service for managing EC2 game servers. Now let's talk about GameLift. So as in the previous slide, you have players that want to connect to game servers. They come in through your game services and then ultimately are managed onto game servers by GameLift. GameLift is comprised of three basic layers. First, FlexMatch is an optional matchmaking service to form player matches based on flexible rules that you provide. Next, Queues is a service that routes players to the lowest latency regions globally. And third, Fleets, which host your game server build on game servers and scale up and down based on player demand. So your players get authenticated, get matched into games either by your matchmaking service or FlexMatch, and then those matches get sent to queues to direct them to the lowest latency fleet to play your game. So that all sounds great, right? Well, what's the cost? So peer-to-peer has one key advantage over dedicated game servers. Dedicated servers cost money. So how do we minimize the cost of dedicated servers to maximize their advantage over peer-to-peer? Cloud services like gamedev have features focused on keeping prices low, so let's dive in and talk about those. Cloud services like gamedev have a major advantage over on-premises data centers. They can access large pools of server capacity so that you are only charged for the servers that you actually need. To leverage that advantage, there are two core features that any cloud service like gamedev has: auto-scaling with target tracking and instance packing. Auto-scaling with target tracking allows you to automatically scale up and scale down game servers to minimize costs while meeting player demand. So here's a graph of player traffic over the course of a day with peaks and valleys in the number of players as they're connecting and disconnecting from your game. If you're running your own data center, you have to purchase a fixed amount of hardware per data center. This results in unused capacity and wasted money as player demand decreases. With auto-scaling with target tracking on gamedev, you set a desired buffer capacity, shown here in yellow, and gamedev automatically scales servers up and down to meet demand and save money. Instance packing allows you to consolidate game sessions onto fewer servers. In your on-premises data center, you have a fixed number of game servers you have purchased upfront, so optimizing how game sessions are distributed across these servers doesn't save you any money. gamedev, on the other hand, will pack game servers onto fewer hosts, allowing unused capacity to scale down and for you to save money. gamedev also allows you to pack up to 50 game sessions on a single host currently. gamedev has a third unique feature to leverage the advantage of the cloud as well as to help customers save money: Spot with Fleet IQ. So let's talk more about that now. So what's Spot? Spot is excess AWS cloud capacity. It's sold at a discount over on-demand capacity. It can be interrupted, and once interrupted, you have 2 minutes to shift your workloads. So how can we use Spot when players want uninterrupted games? So enter Fleet IQ. Fleet IQ is a reactive algorithm that we've developed for estimating instance viability. Every new game session is a new placement decision, so the effect is a continual rebalancing of capacity under the covers. So imagine that we've got our placement queue, and behind that queue we've got two regions with fleets, in this case US West 2 and US East 1. Each of those regions have similar capacity, both spot and on demand. So the first thing Fleet IQ does is it picks the lowest latency region. In this case, the average latency of players in the match that we're trying to place onto a game server is 20 milliseconds for US West 2 and 60 milliseconds for US East 1. So US West 2 is selected. Then we apply instance viability scores to determine the most viable instance type. We sort by the least expensive, and then we select that instance to place the game session. In this case, Spot C5 extra large. Now there are a number of edge cases that come out of this. So what if all fleets are out of viable capacity, right? So what we'll do in that case is we'll actually fall back to the next nearest region, in this case US East 1, and we'll place those instances after doing the same cost assessment that we did in US West 2. In this case again, Spot C5 extra large. And what if the first choice in a region is out of viable capacity? So in that case, what we'll do in order to keep latencies low is we'll place on existing but less viable instances. So in this case, the C5 large instance type became unviable, but we'll continue to place game sessions there while we're spinning up capacity in C5 extra large. Once that capacity is spun up, game sessions will naturally drain out of the C5 large instance type and onto the C5 extra large, where instances are more viable. So essentially then, how does Fleet IQ save costs and keep availability high? So summarizing, queues use Fleet IQ to continually rebalance capacity across instance types and regions to ensure that players are getting both the lowest latency games and the lowest prices possible. So now the money part, right? How successful is Fleet IQ at actually rebalancing? Well, in practice across all customers, we've currently seen a 1 in 75,000 game session interruption rate in practice. So now I've told you all about Fleet IQ. I've talked about GameLift architecture. Let's hear from some customers about their experiences with GameLift. First up, we have Fadi Beirudi, Technical Director of Behaviour Interactive, who's going to dive into their journey to dedicated servers with their game, Dead by Daylight. Take it away, Fadi.
Thank you very much, Bruce, and hi everyone. I'm very excited to do this talk. My part will be to take you through the journey of Dead by Daylight towards migrating to dedicated server. It's going to be a chronology, and let's start in 2016 when we first released the game on PC Steam. Like any multiplayer game, we have to worry about where to put the player profile, how to retrieve it, where to store it, what to do with matchmaking, which network technology to use, and very, very importantly, what is the network topology of our game. So in 2016, it looked like this. The player profile, we used Steam services to retrieve and store the player profile. We used Steam matchmaking. We used Steam Socket for network technology. And as far as topology, our topology for Dead by Daylight was listen server. Moving on to 2017, we ported the game then to PS4 and to Xbox One. So in order to do that, we actually introduced our own backend here. We call it Kraken internally. For player profile, we started using Kraken to store and retrieve the player profile for all platforms. We also wrote our own matchmaking system. As far as network technology, we stayed with first-party network sockets, and I'm going to explain why in a moment. There's a reason why we did this. And we stayed with listen server. Now to network technology. Basically, why did we stay with Steam sockets, PSN sockets, and Xbox Live sockets? Well, precisely because the topology is listen server. But why? So the reason is that whenever we're talking about listen server, whenever we talk about peer-to-peer, we have to have a NAT traversal solution. And whether it's Steam sockets, whether it's PSN sockets or Xbox Live socket, they all had a NAT traversal solution, so we did not have to go and implement our own. So we stayed with this technology. What does this server look like in Dead by Daylight? It looks exactly like the graph I show here. We have one server and 4 clients. It so happens that the server is also another client, and that happens to be the killer. The killer is the server. The clients are the survivors. Why did we do it this way? Well, we have an asymmetric game. If the game has no killer, then there is no game whatsoever. So it kind of made sense that the server was the killer. It is important to specify that Dead by Daylight is not a peer-to-peer game. Peer-to-peer looks like this. If you look at the graph, you see that every peer machine is connected to every other peer machine. Also, every peer takes certain decisions with respect to all kinds of things like movements, interactions, etc. Notice that, for example, Claudette here talks to all the other machines. Notice that the Trapper talks to all other machines, and so is Dwight, and so is Meg, etc. But Dead by Daylight is not a peer-to-peer game. Dead by Daylight is a listen server game. It's important to make that distinction because there are certain issues with listen servers that are the same as peer-to-peer, but it has also other issues. I'm going to talk about this a little bit later. Dead by Daylight looks like this again. Notice that all the clients have only one network connection. They talk to the server. The server, which is also a client and is the killer, has 4 connections and not just 1 connection. And this is also key for later. Why did we choose to implement listen server in the first place? Well, it is much simpler than the dedicated server, so the implementation is simple. all the machines execute exactly the same code, or almost exactly the same code. On Windows, we didn't have to port to another platform. It is just simpler. It's also free. We didn't have to pay for extra infrastructure on the cloud. We didn't have to pay for extra machine. We didn't have to buy anything. Everything runs on the machines of the players. Also, one thing that is probably key is that Unreal Engine supported it out of the box, so we didn't have to do any extra work or write any extra code to make it work. It just worked day one. But probably what nailed it for us at the beginning as far as listen server is that asymmetry makes it possible, and Dead by Daylight is an asymmetric game. If the game was completely symmetric, if all the players were exactly the same and it had perfect symmetry, it would have been very, very hard to justify using listen server, where you had one player who had no ping whatsoever, and all the other players had higher ping. So that player that has no ping would have a huge advantage. In our case, we have one player that has zero ping, but it happens that the game is asymmetric. That player is the killer, and the gameplay of that player is different than the gameplay of the survivors. So we could hide behind the asymmetry. So in short, we went with listen server because we actually could do it. Our game allowed us to do it. So obviously, there are disadvantages to listen server. We wouldn't be here talking about how we migrated to dedicated servers if listen servers had no issues. Some of the issues are the same as those of peer-to-peer issues. We have to have a NAT traversal solution, as we discussed. Latency is high on listen server, the same as on peer-to-peer, higher than dedicated server. But also, listen server has its own issues, has problems that are more than just peer-to-peer problems. So for example, a bad killer machine penalizes survivor. If the frame rate is very low on the killer machine, on the server, then the clients will not get their updates very quickly, and they will considerably lag. So a bad killer machine does not necessarily penalize the killer, it does penalize the survivor. Well, it penalizes the killer is that in the game it doesn't look nice, but the survivors are gonna lag more. And so is a bad internet connection on the killer's side. If the killer has a bad internet connection, the killer doesn't really care. They have zero ping. But a bad internet connection could mean very, very high ping times for the survivor. Another disadvantage of listen server is that the server part of the listen server is actually not just a server. It's a server and a client. So the killer has to execute server code and it has to execute client code. And that makes it even slower. So the frame rate on the server machine is always lower than the frame rate on the client machine. Here's a CPU frame on the listen server, on a typical listen server. So it's not exact, it's more or less what happens. Let's go at the beginning. At the beginning of a frame, we get the packets from all the clients. We have 4 clients, we get all the network packets from all the clients. Then we update the movement. Then we update the interactions with objects and the interactions with other players. Then we do some other logic. We update the animation, we update the physics, we update the particles, and then we send back all the packets to the 4 clients with all the updated data. And we also update the UI. So this is more or less a typical frame. I could have added, for example, that we update the rendering. It's not there, but obviously, it's also part of what happens within a frame of a listen server. So if we notice carefully here, we see that there is client code that needs to be executed. Like, for example, the animation and the local physics and the particles and the UI, and the rendering is not there, but the rendering is client code. It doesn't need to run on the server. So there's client code. There's also server code, like getting the packets and sending back the packets to all of them, to all the clients, and updating the movement. All these authoritative decisions and all the network happens only on this is server code. And there's also some parts that are a mix of both client and server. So both, like for example, the interactions are run more or less on the client and on the server, and some other logic we can imagine also runs on both the client and the server. The point being is that in a listen server frame, there is client code and server code, so it is always longer. So the frame rate is lower on a listen server by definition than that of both a dedicated server or just a pure client. So you see the frame rate for the killer is lower than that of survivors, and the network traffic for the killer is higher than that of survivors, because survivors have to connect only to one machine, that of the server, the killer, whereas the killer has to connect to 4 machines. Okay, let's go back to our chronology. We go back to 2017 again, where this was the landscape. We were on Steam, PlayStation, and Xbox, and we had all this wonderful technology. Now, moving to 2019, we wanted to port the game to even more platforms: Switch, mobile, both iOS and Android, and another PC platform, which is the Windows Store. We stayed, obviously, for the player profile and the matchmaking with our own technology. But what about network technology and topology? So I just said that as far as network technology, Steam, PlayStation, and Xbox implemented NAT traversal in their sockets. Well, that was not the case for any of the new 4 ones. The Switch did not have that. iOS did not have it, Android did not have it, Windows Store did not have it. We had no NAT traversal solution. So if we wanted to stick with listen server, we had to implement our own NAT traversal code anyways. But even more importantly is that a Switch and a mobile are not as powerful as a high-end PC. So I just said in the slide before that the frame rate of the listen server is always lower than that of a client. And in the case of the Switch and of mobile, it was just not feasible anymore. It was just way, way, way too slow. And the network traffic was also way, way, way too high to have a listen server. It was just way too much traffic. So basically, the fact that we needed to port to all these new platforms forced us to move to dedicated servers, and we use standard IP as for network technology for all of them. It's important to note, though, that we were thinking of moving to dedicated servers way before porting to these platforms. It's just that here we couldn't release on these platforms. We couldn't port the game to these platforms if we did not move to dedicated servers. So it was a great occasion to move to dedicated server here. But we wanted to move to dedicated server anyways, because dedicated servers is a better solution in general than that of listen server. Here's how it looks on Dead by Daylight. You have a headless server, some machine that runs on the cloud, and you have 5 clients, and the 5 clients are the 4 survivors and the killer. And notice that now suddenly the killer has only 1 connection. It doesn't have 4 connections, it only connects to the headless server. And we made changes to the code that made it run only client code and not server code. And we made changes to the headless server to run only server code and not client code. So as far as performance, we gained a lot. What is needed to go from listen servers to dedicated servers? Well, the dedicated server in our case runs on Linux, so we had to port it to Linux, compile and run it, remove the client code, as I said, change the game flow to a simpler flow of the dedicated server. We had to make many, many gameplay adjustments. This was probably the biggest part. We're changing the way the game is being played here. So we had to work a lot on gameplay, and we continue working on gameplay today and in the future to adjust more to dedicated servers. We did a few changes to the matchmaking, and a big chunk of what we would have had to do was to develop live services. And I'm going to go more into details into what this means and what it entailed. So in order to develop live services, for example, we had to write code to start up, monitor, and shut down server processes automatically. Same thing for server machines. So on one machine in the cloud, you can have multiple processes. In the case of Dead by Daylight, right now we have 4, more or less. So one machine, multiple processes. We had to write code to be able to start them up, to shut them down, to monitor them, to see if they're still running, if there's a crash, all kinds of stuff, all kinds of logs, etc., etc. We had to implement auto-scaling. When more players want to play the game, we needed to have more machines and more processes be ready automatically. And when less players are playing the game, we had to scale down. We would have had to do that. We had to write a lot of tools in order to monitor everything, to have statistics, to monitor costs, and all kinds of stuff. So when we scoped it before we did the work many years ago, we said this part will take us about 6 months of work. In retrospect, I think today that we were very optimistic. Maybe we would have had a basic version running in 6 months, and even then, but to have a real solution would have taken us more than 6 months, much more than 6 months. The good news is that we did not have to do it. And this is the reason we didn't have to do it, because instead of developing live services, GameLift did all the heavy lifting for us. All this came with the GameLift solution. What we ended up working on was, we worked about 4 weeks to be able to connect the Dead by Daylight server with the GameLift services. So, getting the callback from GameLift, spawning, making sure that the machines are being spawned and the processes are being spawned correctly. It took us about 4 weeks. We add 2 weeks of extra tooling. So all in all, 6 weeks of work, and we were all functional instead of at least 6 months and probably much, much more. So we're very happy to have the GameLift solution available at this point in time. Here are some numbers that compare dedicated servers ping to the listen server. The median used to be about 90 milliseconds. On dedicated servers now it is 60 milliseconds. This means that 50% of the players used to be lower than 90 and the other 50 higher than 90. Well, now it's 60. 50% is lower than 60 and the other 50% is higher than 60. Much better. The 75th percentile went down from 160 to 80. So think about that for a second. Before, when we were on listen server, we had about half the players lower who had ping time lower than 90. Now we have 75% of the players who have a ping time that is lower than 80. Much, much better. Much better. 95th percentile, we also went down considerably from 300 milliseconds to 150 milliseconds. However, not everyone was happy. As you can imagine, the killers used to have 0 ping. Well, now they have a normal ping like everybody else. So the killers complained a little bit about the fact that, the game feels different and everything. So which is why we had to actually do a lot of gameplay work and a lot of gameplay adjustment to make sure that the game still ran correctly. But the killers used to have 0, and now they don't have 0 anymore. Here are some pre-COVID numbers. 700,000 games a day before the pandemic. What's interesting is that we had, in general, no spot interruptions whatsoever in the last weeks up to the pandemic. We almost never use on-demand machines. It was almost always using spots, and we had no spot interruptions, so it was great. It was really good. We still kept 10 to 15 active on-demand instances per region. We were thinking about reducing this number. We ended up not doing so, actually. Because post-COVID things changed a little bit. So now instead of 700,000 games a day, we have 1.2 million games a day. And suddenly we start having a few spot instances interrupted. We see a few more than we used to. We used to see none. Now we see a few. We have about, like, for example, in the last 2 weeks, we've had 10 to 15 games being interrupted. It still is a great ratio. It's about 1 in 1 million. So it's actually better than the 1 in 75,000 that GameLift says it. Usually we have. They say it's 1 in 75,000. Well, in our case, it's actually the experience was better than this. It's about 1 in 1 million. But we also see more on-demand machines than before. We don't run exclusively on spot now. We run a little bit of on-demand, but we're still overwhelmingly on spot though. We are looking to set up more advanced scaling rules and develop more tools and automatic alerts. 10 to 15 on-demand machines available, waiting to scale up with our scaling rules was a very naive strategy. With that strategy, we would have had, if we had, for example, a sudden drop in spot instances and a sudden need for on-demand instances, we wouldn't have been able to scale up correctly. So we're changing, we're trying to set up some more advanced scaling rules in order to make sure that everyone gets to play very, very quickly. We're also trying to develop more tools and automatic tests. For example, if one region there's a problem with spot instances and we can only go on demand, we're trying to get alerts to be able to reroute players to a different data center. And so yes, we're developing these tools in order to protect ourselves now that we have more players playing the game than before. And that's about it for me. Thank you very much. It was a pleasure to talk to you. We are hiring. If you're interested, please go and visit our website. Thank you. Bye.
Thanks, Fadi. It was great to hear how using spot instances on GameLift was able to save you guys development time and money overall without resulting in interruptions to players. That's some great data. Next up, we're going to hear from Laurent Chouinard, services producer from Ubisoft, who's going to talk about their experience using GameLift with their game, For Honor. Take it away, Laurent.
Thanks, Bruce. So I'm going to tell you the story on our side, on For Honor, on how we made the switch to spot instances. We were also, initially, we shipped our game on peer-to-peer, and we also made the journey to converting to peer-to-peer. So I can understand also the challenges that it brought to Fadi's story, and we're really relating to that, right? And it's cool that now we're on dedicated servers. So we launched the game in 2017, and we made the switch to dedicated server on 2018 in February. So we've been using only dedicated servers now for 2 years on Amazon GameLift as well. So let's start by recapping a bit of the story between Amazon, the GameLift team, and us on For Honor, following our shipping of the platform on GameLift. Now they came to us and said, you guys, after a bit of using in production, they said, you guys, you should use Spot, right? And we were a bit wary about that. We're like, well, there's no way to see if using Spot would affect players. And then you say that there's going to be a possibility of recall, and we're not ready for that. So the GameLift guys went into work, and they came back to us and says, we added some Q metrics now. And these Q metrics are going to show you if the first placement fails. So you're going to be able to see when you're going on Spot and not. And further, we're going to also have you a fleet metric into CloudWatch so that you can see when there's a recall. So you can tell if there's an impact to players. And we're like, well, yeah, but the 2 minutes that you give us as a head start warning to remove players and in case the instance gets recalled, we think it's too short. With 2 minutes, there's not much we can do. Most of our matches last much longer than 2 minutes. And at the end of the match, players can rematch against themselves and continue fighting. So actually, many more matches can occur one after the other. So if a recall comes, we would be killing these players eventually. And we really don't want that. We don't want to have failures that are going to be perceived by players. It's not like you can just reconnect to the match and continue. You're in a duel, you're fighting a few seconds, and that's it. So the GameLift team went back to work and came back to us later, I believe it was a few months later, and said, all right, now we got it, guys. We crunched the numbers. We ran all the simulation. We watch in real time what happens. And for you guys, we are predicting that you would not have more than 0.001% of probability of recall. Now, this is super low. All right, fine. We decided that at that point, it became a viable choice for us. It was a good deal to try to see if Spot could work for us on For Honor. Now, of course, why bother? It's rather simple. At face value, it's simply because the instances are much cheaper when you use them in Spot rather than on computing, on demand, sorry. For example, in London, a C4 large, which is the type of basic instance that we use to host games, it's 50 cents an hour. That was, at the time of writing this slide, the public price on the website was 50 cents an hour. And if you do the exact same Linux instance in Spot, it's 3.5 cents an hour. So it's much cheaper. 76% rebate on computing costs. That's very appealing. So that's a great reason for us to move forward and try it. So how do we use that on For Honor? Let's see first with the on-demand how we were set up. Now our matchmaker is already locating players in the areas that are best to play together. So in this example, our matchmaker is choosing 8 players that wants to play in a match, and it's placing them in Europe West. That's the best location for them to play. So it goes to the GameLift queue and in that region and says, please give me a server for these players now in this region. And if there's capacity, the GameLift queue is going to pick the first one, the on-demand fleet, in the same region. And for all of our regions and all of our queues, we set up a backup. In case something happens in this region and it's full, then there's a backup in similar region, which is EU West 1, which is a bit further away, a good backup in case the first one doesn't work. So that's the basic setup that we had worldwide. Now, to do that for Spot, the only difference would be that at the top of the queue, we place a Spot fleet in that region. So if there's capacity and the Spot fleet is viable, then place players there is going to be cheaper. If for some reason it's not viable or there was no capacity, we continue to try to aim for Spot in the backup region, as we did before in the on-demand flow. And if it doesn't work, well, we go back to on-demand as a pure backup in the same region, but this time more expensive. That seemed like a pretty rough first try that would give us good results. It seemed to work, right, on paper. And we delivered that. We tried it in some regions. We increased the number of players progressively. We rolled it out progressively. And eventually we had problems. And the way the problems occurred was, first, well, everyone is happy. It works well playing. And then in this example, we're using European sites. So something happens in London. The London data center of Amazon has something going on, a change in pattern that makes Spot to become unviable. That's perfectly normal. That's how the system is designed. When Spot becomes unviable, we're rerouting. And for us, we were rerouting to Frankfurt, the alternate European site, still on Spot. But then that causes an unexpected sudden increase in Frankfurt because from 0 to all players, the infrastructure is seeing a rush of new players in Frankfurt that was not following the patterns as before on that day. So, well, Frankfurt Spot becomes unviable. We're kind of the cause of that because we just dumped a few thousand players in a minute's notice. Of course, the algorithm behind Spot is going to say, it looks like this site should not be viable for Spot anymore because there is a sudden increase. Becomes unviable means we are rerouting to London. So far, this is by design, and this is all normal. We should not have a problem because if all Spot places are taken, then we go to on-demand and it works well. That's what we did before, right? But then the on-demand fleet was idle because every player was into Spot. There was nothing in on-demand, so the fleet was scaled down to the minimum with a few spare instances to accommodate players. But at that point, the scaling is unable to ramp up rapidly to the number of players that are demand. So we can't place players anymore. Everyone's mad. It's not working. All sites, all fleets, they're rejecting players, either because Spot is not viable or because the on-demand is unable to scope to scale up to meet demand. Eventually, this problem fixed itself after a few minutes. I believe it was 20 to 30 minutes for the systems to catch up and scale up, but it would be a quite damaging moment for players to have to go back to matchmaking and wait a bit more until they get a server for them. At that point, it seemed obvious that the problem was scaling. Scaling is unable to push the on-demand fleet that was idle to meet demand. We went and discussed with the cloud experts, the Amazon team. We obtained that the answer that was in the discussions was very interesting because it seemed super simple in just add more buffers. It's simple. If your on-demand fleet is unable to scale up, then it needs more buffer. Just put more instances idle so that when there's a fallback, you have room. Makes sense, let's do that, but wait a minute. We're saving money by using spot instance, but we're gonna spend more by having more buffers on the expensive on-demand side. In the end, it seems to balance out and we're kind of negating our savings with more cost. So let's dig deeper and see what actually the problem is. Now, we know that the autoscaler is following the load. Now, that's our own autoscaler. We made our own algorithm to scale the fleets, but it's very similar to the one that gamedev does with the rules that are applying. If you have a capacity below a certain threshold, put more instances. And when you design scaling rules like that, you realize quickly that you have to do things differently for a low volume fleet than a high volume one. If you're in a low use, you want small scale-ups because you're accommodating a few players entering progressively because you're probably at the beginning of your daily curve. But when you're at the heavy use, at the top of your daily peak, you need to scale up more aggressively because you're receiving much more players. So the rules are adapted, and that's how we designed ours. We're doing small scale-ups at low use, high scale-ups at heavy use. But then when a non-viability event happens in spot, it doesn't happen in the middle of the night. It tends to happen exactly at the peak moment of the day when it's at the heaviest use. So your spot fleet is using the large fleet rules and your on-demand fleet is using the small rules because it's idle. Therefore, your small rules are unable to recover the way that the big rules were doing. And also, an important point, there's no way to kickstart the scaling. It's too late. It became unviable now. So even if we order a bunch of instances, they take minutes to come live. And these minutes are gonna be lacking because the switch goes instantly. We're going from spot to on-demand right now. So even though it takes minutes to bring new instances, you're not gonna have time to have them because they're filled up. You're in your peak time, so you need many instances. So the problem seems to be around the concept of viability. And what's viability in the sense of spot? Basically, the way I describe it, I have a tendency to dumb things down a bit and make them easier to understand. And for me, Fleet IQ is basically computers watching computers. Or more precisely, it's gamedev watching the placement requests that we make into the data center, plus the rest of a data center usage and the statistics around the normal patterns of usage of this data center, which allows the machine learning in Fleet IQ to produce a risk of recall. It's outputting in real time a percentage that is either, well, it's more probable that you're going to have a recall, or it's less probable that you're going to have a recall. And this was used in the yes-no sense. Actually, let's, without going into the exact numbers, because I don't know them, but the way we figure it is that between 0% and 0.00 something percent probability of a recall, it's super low, so use spot. You can use it because the probability is tiny. And if it's above that percentage of probability that you're going to have a recall in the future, then don't use spot because it's becoming probable that you're going to have a recall. Let's be conservative and don't use it. But is 0.000 and 1 more percent safe? I mean, it's a tiny fraction difference than before. Now, the way spot used to work was that it would actually be a yes-no problem and it would become instantly not viable anymore. But what we see is that viability in itself, it's not a yes-no problem. It's more like the weather. it may or may not rain, there's more probability, so you take more precautions as the probability increases, but it's not going to be a yes-no answer. The solution in the end was super simple. The queue, when it places into the first spot fleet and it's unviable, goes to the backup, goes to the on-demand, and it goes all the way to the bottom of the queue. Normally, it was stopping there. There was no placement, it would stop. But now, the change that we made, that GameLift made, is that if at the end of the queue there's no place available, it goes back to the top, and this time, any unviable spot fleet that has capacity is going to be used anyway. The idea is that it still has capacity, and the probability of a recall is only tiny bit higher than before, so it might still be safe, or at least safe enough to continue using while the on-demand fleets are ramping up their capacity and preparing themselves to receive the rest of the players. So now, the way our flow is set up today is, for the same example, where we're trying to place 8 players in Europe West. It goes into the fleet, it goes into the queue, and it starts at the top. If it's viable, go to the spot. If not, go to the on-demand. And then go to all the steps. And at the end, if it's not working out because there was no way to place the players, go back to the top. And when there's capacity in a spot fleet, go anyway. Now, it's important to say that we've been, since the beginning, very careful about having impacts to players. We really want to protect the experience of players and not have recalls or have them like in the most tiny fraction of a percent possible. So we made the calculations, and the actual recall rate today, now we've been measuring for 1 year because we've been switching, we've switched to spot exclusively since a year ago. So for a year, all of our games, we've measured the total number of times that a game was recalled that had players on it, so an impact game, with the total number of games that were played in the perception of players. That gives us a percentage of the actual recall rate. And for us, it's, and drumroll, 0.0000002, 63%. Actually, it's more like 1 out of every 380,000 games is recalled, for real. So the takeaway for us after this fix is that, well, there's some downsides. Tiny, but to be considered. There's a bit more complex deployments. Since we are pushing more fleets, more configuration, then that means that the deployments are more complex. There's more fleets to take care of in more regions. All of that adds complexity to our deployment pipeline. There's a bit more wasted idle instances. Since when we are waiting for players to arrive in a fleet that is going to act as a backup, there's some idle instances there. So if we add backups to everything, well, we have more idle instances, and that means more waste. So even though the switch seems drastic, the savings are a bit less. The autoscaler that we wrote, or that any team would have to manage, now has to manage more things because there's more fleets to watch for, so there's more scaling to do. We also have increased the fragmentation of players. The idea is that if you're using on-demand and then you switch to spot, there's still players on the on-demand. And then when you switch from spot back to on-demand, there's players in the spot. So in the end, all of your players can be fragmented to more fleets. And more fragmentation means that you might have a bit more waste in these fleets or these instances because they're not packed as tight as if you were using only one. In the end, that's marginal, but it does add a bit of overhead to your savings. And one thing that, it seems obvious now, but at the time of implementing Spot, we're focused on that 76% cost reduction, but in the end, it's 76% of computing cost reductions. It's not a reduction of your bandwidth. And on our side, bandwidth is still a significant part, like we're about half and half in computing and bandwidth. That means that the savings is proportional to the portion of computing. It's still important, it's still a huge savings for us and we're very happy. But we realized back then that we had forgotten about the bandwidth. On the light side, of course, it's a drop-in replacement. For us, it was super simple, some reconfiguration and you can switch from on-demand to spot. It's only parameters, so that's easy to experiment. And also, we were able to implement this change progressively we changed certain regions first and then laid out the rest of the world to use that so that we could mitigate risk in case of something bad going with it. And it did, so we were able to contain that discovery of a problem to a single location instead of going worldwide at once. So the drop-in replacement is really cool. There's the bailout mechanism. Now, for us, we're unable to use that mechanism. Let me explain. The way Spot works is that it's telling the instances, if I have to recall you, I'm giving you 2 minutes head start. That's really cool. You have 2 minutes to clean your stuff, shut down cleanly, and move players somewhere else. But for us, that's not possible because we have matches that last way more than 2 minutes. The shortest match, if you're really good in a duel, maybe you can do your match within 2 minutes, but that's it. Every other type of gameplay we do on For Honor is going to last more than 2 minutes, but further than that, you have the possibility to rematch. And when you rematch, we don't disconnect players from the server. We keep them right there because we want that instant go back into fighting mode. Everybody is connected together. They've got the voice chat going, so we just keep them and throw them back into another session of the gameplay. Therefore, they're still on the server, and the server is gonna live for much longer than that. Therefore, we don't have a way to bail out these players within 2 minutes that would not have an impact to them. Also, there's price bidding available that allows you to have more, or rather more flexible savings, let's say. In the sense of, instead of using just one instance type as a spot, you can have multiple. For example, we use the C4 large, but we're also introducing the C4X large into our fleets so that we can have the possibility of using those as spot when the other ones are not available. It's not that when one is unavailable, nothing is. It's just that type. So we're going to experiment right now, and this is something we're introducing this year. We're trying to play with different instance types to see if we can shape our savings differently depending on the data center and the particular usage patterns of that region. Of course, in the end, it's very cheap. It's also one of the biggest cost savings that we've done after introducing the multi-tenancy and packing the instances and switching to Linux. The remaining savings that was making a significant help for us is switching to Spot, and we're very glad that we were able to do that. And as our tests have confirmed, and as the data showed for us, the impact is negligible, and so negligible actually that when we calculated initially the first numbers before, now I gave the number for after a year, but after rolling out our tests initially, we calculated a similar value, and we computed that if we fix any of our top 10 bugs in the client or server, it would have a better impact to players than the switch to Spot instance had on the negative aspect. And we kind of did that to compensate so that in the end the experience is better, because we've allocated some effort to fix some bugs. Of course, we always do, but we put ourselves into the mindset of let's fix one so that the impact of going into Spot after that is negated and the overall experience remains the same or actually better at all time. So that's it for our journey. That's how on For Honor we made the switch to Spot and are currently having all of our games on Spot fleets worldwide. Thank you.
Thanks, Laurent. It was great to work with you folks to improve our fleet IQ algorithm early on and to make sure that we were keeping costs low for you guys. And to see that interruption rate as low as it was, that just blows my mind every time. Wow. Great to hear that For Honor players were having a great experience with GameLift and Spot and Fleet IQ. All right, thanks Fadi and Laurent for taking us through your journeys using GameLift. Some really good stuff there around why GameLift makes sense over building your own infrastructure and what your experiences were with minimizing costs with Fleet IQ and Spot and decreasing player latency. Thanks to both of you. So let's recap. Why should you use Amazon GameLift for hosting your dedicated game servers? Well, as Fadi and Laurent showed us, there's no compression algorithm for experience. Building your own infrastructures is hard. Low latency with queues. GameLift supports 15 regions today with more on the way, and low-cost game servers with Spot with Fleet IQ. Save up to 70% compared to existing on-premises deployments. You get high availability, low maintenance, auto-scaling, matchmaking with FlexMatch, and a ton more. Before we get to Q&A, I wanted to talk more about that new lift and shift option that we have for leveraging your existing infrastructure to use Fleet IQ, which we are simply calling the updated GameLift Fleet IQ, which is now publicly available in preview. We've taken the same low latency, low cost Fleet IQ algorithm and have pulled it out of managed GameLift so that you can plug it into your existing game server management infrastructure and start lowering the cost of running your dedicated game servers faster and with more flexibility than ever before. You can onboard server workloads to the cloud with your own tools and independent of adopting any other managed GameLift features. You can save on costs, speed your time to market, and deliver a reliable player experience. And you can gradually move your existing or new games to the cloud with all of the benefits of EC2 Spot instances and GameLift Fleet IQ's session reliability management. So to wrap up, I want to once again thank our presenters, Fadi Beyroudi from Behaviour and Laurent Chouinard from Ubisoft for diving into their experiences with GameLift. Thanks a ton to both of you. And to our viewers, please feel free to explore other sessions. If you have additional tech questions, stop by the Ask the Expert section to speak with AWS tech experts. For more details on this presentation, check out the Resources Center. And with that, we're happy to answer any questions you might have.